Welcome back. We're still looking at ionic compounds in this new section, but we've turned up the complexity a little bit. In addition to ions that you find on the periodic table, there is another group of ions that we can use, which are the ones in this box at the top, the table of common polyatomic ions. Each of these is a group of atoms stuck together which collectively have one charge, which they give to you on the tail end. So, for example, nitrate in the middle of this list is a nitrogen and three oxygen atoms all stuck together in a lump, and all of that together has a charge of -1. And there are a host of others that we can use. Other than that, they follow the same rules as other ionic compounds, which means we have to do a little bit of math in our heads to make the formula come out right. So let's see what we're talking about with that. If you have something like sodium nitrate, we need to know how much positive charge is on sodium and how much negative charge is on nitrate. And this page can answer both of those questions. Sodium has a charge of +1. Nitrite is right under the nitrate I gave as an example. It's NO2 and has a charge of -1. I know that's a bit of a stretch to read on the screen, but I trust you have your data book right next to you and it'll have these in nice print. So we are linking together sodium ions, which look like this, and nitrite ions, which look like this. And happily, the charges match here. We have +1 and -1. That's exactly the kind of thing we want, is the same number. So the formula for this is very simple. It's just NaNO2. Now the second one also goes very smoothly because, spoiler alert, the charges there also work out nice. Magnesium has a charge of +2. It's Mg2+. And carbonate, you'll find on your list right here, it's CO3 and has a charge of -2. So we're combining magnesiums with +2 and carbonates with -2. Again, same number, so our formula is very simple, MgCO3. So far so good. I feel like our luck's about to run out and the difficulty is about to increase. I'll get to these in a moment. Let's do all the ones where we're going English to formula first, and then we'll take care of the formula to English ones later because they're easier. Calcium permanganate. Calcium is element number 20. It's right here and has a charge of +2. Permanganate is third from the bottom in our polyatomic ion list. It's MnO4 and has a charge of -1. So we're combining calcium ions and MnO4s, which have a -1 charge. Here we don't have a charge match. We have +2 and only -1. We need equal amounts of those, which means we need another permanganate. If two permanganates gang up on a calcium, then we get +2 charge here, a total of -2 charge from these guys combined, and now we have a compound that will work. So when we write this formula, here's the wrong way to do it. CaMnO4 2. The trouble with this is that it looks like O42. This 2 is supposed to apply to the entire permanganate, and the way you make that happen is you bracket the entire ion. Now this means a single calcium ion and 2 sets of MnO4. So anytime you have multiples of a polyatomic ion, you need to bracket it, otherwise this 2 won't apply the way you want it to. It has to extend over the entire ion, not just the last thing in it. Yttrium hydroxide. Yttrium's a pretty rare element, but I was trying to do something you haven't seen before. Yttrium is element number 39, and its charge is +3. So we get Y3 plus for yttrium. And hydroxide, careful, if you just have H, that is called a hydride. If you have hydroxide, that's something else. It is OH, and it has a charge of -1. It's a polyatomic ion. So we have yttrium ions and hydroxide ions. There we go. Again, our charges do not match. We have +3 and only -1. So to make this work, we would need 3 hydroxides. You don't have to write this out. I'm just doing it to hammer home the point that here we have 3 positive charges, and these guys working together bring 3 negative charges. So we get a valid compound from that. And the formula would be 3. What's missing? You need the brackets again. If you just write this, it means a single oxygen and then 3 hydrogens. We need this to show that there are 3 of the entire hydroxide. This means an yttrium atom, 3 oxygen atoms, and 3 hydrogen atoms, because the 3 triples everything that's inside the brackets. One more of these. Lithium sulfate. Lithium is element number 3. It's right there, and has a charge of +1. And sulfate is on your polyatomic ion list. It's SO4, and it has a charge of -2. So, lithium ions are +1s, sulfates are -2s. Our charges do not match. To make this work, we actually need another lithium. So now we have 2 lithium atoms and a single sulfate ion, or 2 lithium ions and a single sulfate ion. So for our formula, we have to write lithium, 2 of them, and then a sulfate. Because there's only 1 sulfate, there's no need to bracket this. In fact, you should not, but we do need 2 on the lithium. Fair enough. Now going the other direction is actually easy, just like it is with any other ionic compound, because all you have to do is say the names of the 2 ions. There's really no math involved. For this, the 2 components are Be, which is the element beryllium, and ClO3, which you will find on your list here. It's chlorate. Careful, chlorite is a different thing from chlorate. There's single letters can make a huge difference when you're naming these, so if you don't find something that's a perfect match spelling-wise, worry. It probably means you've missed something. So chlorite would be ClO2, chlorate is -3, that's our guy. And this compound, all you have to do is say beryl, 2 L's in beryllium, I had to think about it, beryllium chlorate. It doesn't matter that there are 2 chlorates. It doesn't matter what the charges are on either of them. You just write beryllium chlorate and you're done. For this, Sr is the element strontium. I say strontium, I've heard strontium too. Honestly, not sure which one is more correct. And Cr2O7 is on your polyatomic ion list. It is second from the top. It is dichromate. So strontium dichromate will take care of this one. Zr is zirconium. Zirconium. And SiO3 is, I want to say silicate. Is it silicate? Yes. On your list, it is here. SiO3, and it has a charge of -2. Not that we need to know that, because when you're doing the English name, all you have to do is say zirconium silicate. You don't have to do any math. All the math is done by the people who are writing the formula. Those are covered. H2O2. This, you might be thinking dihydrogen dioxide, and that's not a terrible answer, but there is actually an ion that can do the same job, and you'll find it on your list, and it is, where is that little thing? Ah, here we are. Second from the bottom is peroxide. Anytime you have a pair of oxygens together with things attached to it, you can call that a peroxide ion, and so H2O2 can be also referred to as hydrogen peroxide. And this one's different. NH4CN is made of 2 polyatomic ions. NH4 together is a positive ion. Second on the list, it is ammonium. It's one of the very few that has a positive charge. So our positive thing is ammonium, and our negative thing is the CN, which is third from the top. CN is cyanide. So this last thing is, for once we don't have a metal in the first position, we have ammonium cyanide. So yes, most of the time the positive ion is a metal, but it doesn't have to be. From now on, you may occasionally see ammonium out in front, and that's okay because all this has a positive charge. You can have this as your positive and another ion as your negative, and that all works fine.